Welcome friends, Igor is here, and in this video we will discuss linear transformations. In this lesson we will define linear transformations between vector spaces, consider examples of linear transformations, and observe that linear transformations take zero vector to the zero vector. Let's get started. On a loose level, linear transformations can be thought of as functions from a vector space to a vector space that preserve the operations of vector addition and scalar multiplication in the vector spaces. Formally, a linear transformation is a function t from a vector space U to a vector space V which satisfies two conditions. The first condition says that t takes the addition of vectors in the vector space U into the addition of vectors in the vector space V. On the left-hand side, the plus sign stands between two vectors of the vector space U, therefore it corresponds to the operation of vector addition in U. But on the right-hand side, the plus sign stands between two vectors of the vector space V, therefore it corresponds to the operation of vector addition in V. Similarly, for the scalar multiplication in the second condition. On the left, we have a scalar multiple the way it is defined in U, while on the right, it is the scalar multiple the way it is defined in V. Here is a visual illustration of these two properties using so-called commutative diagrams. If we start at the top left corner, we can take an ordered pair of two vectors in U, U1 and U2. There are two ways in this diagram to arrive to the bottom right corner of the vector space V. First, we can go down by using the operation of addition in the vector space U, and then we can apply the linear transformation t. This path corresponds to the left-hand side of the equation. On the other hand, we can go from the upper left corner first to the right by applying the linear transformation t to each of the individual vectors, and then go down to V by applying the operation of vector addition in the vector space V. This is the right-hand side of the equation. The reason this is called a commutative diagram is because the left-hand side of the equation is equal to the right-hand side of the equation. In other words, it doesn't matter which path you take, you always end up at the same point. Here's a similar illustration of the scalar multiple property. Please trace your steps in this diagram to see that the equality of the left-hand side and the right-hand side in the equation means that this is a commutative diagram. Here's an example of a linear transformation from the vector space C3 to the vector space C2. The domain is C3, therefore this transformation takes column vectors of size 3 as inputs, and codomain is C2, therefore the values of this function are column vectors of size 2. Let's check that this function is indeed a linear transformation. First, let's compute what happens when we apply t to a vector x plus vector y. These are inputs, therefore they come from the domain. They are column vectors of size 3. We apply the operation of vector addition the way it is defined in C3, and then we use the definition of the function t to compute the value of this function on this input. Finally, we algebraically simplify the result. Let's compare now what happens when we compute t of x plus t of y. First, we compute the values of the function t on each of the two inputs. Now you see that the plus sign in this expression corresponds to the addition of vectors in the codomain, the vector space C2. We apply this operation and we simplify the result. But if you look at the two results, you see that we got identical vectors. Therefore, t of x plus y is equal to t of x plus t of y. This verifies that this function t respects the vector addition. We also need to check that it respects scalar multiplication. So let's compute the value of t on the input alpha x. To compute this value, first, we apply the operation of scalar multiplication in the domain. Then, we use the formula for the function t to compute the value on this input. This is the result of this computation. Now, let's compute the value of the expression alpha times t of x. In this case, we first compute the value of t on the input, and then we apply the operation of scalar multiplication in the codomain. We simplify the expression, and we notice that we got the same vector. Therefore, t of alpha x is the same as alpha t of x, and this shows that this function t also respects scalar multiplication. We checked the two conditions for a linear transformation, and therefore this function t is indeed a linear transformation from C3 to C2. Here's an example of a function which is not a linear transformation. It may seem that this is a nice linear function based on what you know from calculus, but let's see what happens when we try to compute some sample values. For example, let's compute a scalar multiple of the value of s on the vector 1, 2, 3 by the scalar 3. First, we compute the value of s on the input vector, and then we scalar multiply this by 3. Let's compare this with the value of s on the scalar multiple of the vector 1, 2, 3 by the scalar 3. In this case, first we take the scalar multiple, and then we compute the value of the function. But now you see that two results are not the same. They differ in the third component. This means that the function s is not a linear transformation. Can you recognize what part of the original definition of the function s caused this trouble? It is the presence of this term -2. Here is a slightly more involved example of a linear transformation. Let's define a function t from the vector space of polynomials of degree at most 3 into the vector space of matrices of size 2 by 2. First, let's compute the value of t on the input x plus y. The inputs are the vectors in the domain, so we're dealing with two polynomials. Let's represent the vector x as a polynomial with coefficients a1, b1, c1, d1, and y as a polynomial with coefficients a2, b2, c2, and d2. First, we apply the operation of vector addition in the domain, and we know how to add two polynomials. And then we compute the value of the function t on this input by using the definition of the function t. Now, let's look what happens when we compute t of x plus t of y. First, we compute the value of t on each of the two polynomials, and then we apply the operation of vector addition in the codomain, which is the vector space of 2 by 2 matrices. But we got identical results. Therefore, t of x plus y is the same as t of x plus t of y. Now, let's check scalar multiplication. First, let's compute the value of t on a scalar multiple of a polynomial x by scalar alpha. For this, first, we take a scalar multiple in the space of polynomials, and we know how to do this. We scale each coefficient of the polynomial. Then, we compute the value of t on this input. And now, let's see what happens when we compute alpha t of x. Here, first, we apply t to the polynomial, and then we take the scalar multiple in the codomain, the vector space of 2 by 2 matrices. But if you take a careful look at the two outputs, you will recognize they are the same matrix. Therefore, t of alpha x is the same as alpha t of x. This verifies that this function t respects vector addition and scalar multiplication, and therefore it is indeed a linear transformation from P3 into M22. One last observation. Let's prove that every linear transformation always takes 0 vector to the 0 vector. In principle, the vector spaces u and v could be different, and therefore we're dealing with potentially two different 0 vectors. One 0 vector comes from the vector space u, another 0 vector comes from the space v. To have a clear distinction between these two vectors, I will use subscripts to indicate whether the 0 vector comes from the space u or from the space v. So we start with the value of t on the 0 vector in the space u. Let's recall that a scalar multiple of the 0 vector by any scalar is still the 0 vector, so in particular, the 0 vector in the space u is equal to its own scalar multiple by the scalar 0. But then we use the property of linear transformations that it respects scalar multiplication. What we got here is some kind of vector in the vector space V, which is scaled by the zero scalar. And we also proved that in any vector space, if you scale any vector by the zero scalar, you will get the zero vector of that vector space. Therefore, this scalar multiple is the zero vector in the vector space V. But this is exactly what we were trying to prove. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will learn that linear transformations can be performed by matrix multiplication. I will see you later.